Hello, everyone. Today's lesson is on vectors in the plane. So vectors in the plane. So as you know, in the regular two-dimensional plane, x, y, every vector is recognized by 2 points. So if I have a vector like this, suppose this point in the beginning, the initial point is P, and the terminal point is Q. Now I have a vector. The vector which starts from P and ends at Q. There are different ways to show that. One way to refer to this vector is writing PQ and an arrow on that. Or I can give a name to this. For example, I can give a name like lowercase u. So there are infinitely many vectors in the plane. As you have seen in this slide, or as you are watching now, you see that a vector has two important components, two important things related to a vector. So let me draw a vector. Suppose this is a vector. Initial point P, terminal point Q. One thing about this vector is its length. So length of a vector. The other name that we might use is the magnitude of the vector. Like, for example, this vector that I draw here, or this vector that I draw here, both of them are larger than the vector PQ. Obviously, they have bigger length. Or this vector, this also has a bigger length than PQ. So one thing about vectors is the length, how long the vector is. That's an important thing. The other thing about a vector is its direction. The direction of a vector is another important piece of information that we have about a vector. So this vector and this vector that you see in the picture, like we call them, one of them u, the other one vector v, they show different directions. And as you see as you can imagine, in the plane, we have infinitely many directions. One important thing that we should keep in mind is, let me go to the next slide and explain that. Suppose I have a line in the plane and two vectors, they show opposite directions. This vector u and this vector v. Obviously, they don't have the same direction. They have opposite directions. However, these two vectors are still considered parallel. I'll talk about parallel vectors very soon. So these two vectors, they have different directions, although they are considered still parallel. Okay, before talking about parallel vectors, let me talk a little bit on basic things related to vectors. So in the plane, two vectors might be in different positions, but still they might be considered equal. So this vector and this vector, they are equal. Can you guess when two vectors will be considered equal? As you might have figured out, or you might know from before, that these two vectors are considered equal if they have the same length and the same direction. So let me write the definition here. Two vectors are equal if they have the same length and the same direction. So in the picture that you see on the top, U and V, suppose that both of them have the same length and they are showing the same direction. When I'm saying the same direction, as you saw, they are pointing the same direction. And what is important to know is the lines which contains both of these two vectors, they are parallel lines. So these two lines are parallel. And of course, they show the same direction. So these two lines are parallel. So in this picture, in fact, vector u is equal to vector v. They have the same length. The length of u and the length of v are equal, and they are on parallel lines, show the same direction, so they are equal. Obviously, if the lines that they were on are parallel, but they should opposite directions. Suppose these two are parallel lines. And the two vectors, one of them, suppose it's like this. The other one, the same length on the other line, but opposite direction, then u is not equal to v. So if they are on parallel lines, but they show opposite directions, the same length, of course, they are not equal. However, in this case, u is equal to negative v. We'll get back to this later. But keep in mind that in this picture, I assume that the lengths of U and V are the same. They have the same length. They are on parallel lines, and the directions are opposite. So because of this definition that we have here, the two vectors are equal if they have the same length and the same direction. When I draw any vector in the plane, so suppose I draw any vector, say this vector U, there are infinitely many vectors equal to U. So I can draw some of them here. So this is, let me call this V. This is also equal to U, the same length, showing the same direction. This as well, the same length, let me call this W, the same direction. And as many as you want, infinitely many. And all of them is because of this definition, because two vectors are considered equal if they have the same length and the same direction. They don't need to be in the same position. Okay. But we need to show vectors algebraically using numbers. Therefore, we need some notation to show vectors using numbers. Now look at this example that I have this vector in the plane. I said in the plane, so there is a coordinate system involved. Assume that this is the coordinate system that we have, X and Y axis. Let me draw a vector initiating from the origin and equal to vector U. So it initiates from the origin parallel to vector U and the same length. I call this vector V. So I drew a vector from the origin of the coordinate system. Its length is the same as the vector U and shows the same direction. So the initial point is the origin. It is 0, 0. We know that. And the terminal point, suppose it is point AB. So this vector V is equal to vector U. It initiates from the origin 0, 0, and it ends at point AB. One way to show this vector, we use a notation which is pretty standard. So we show V by this notation. So this notation means that the initial point is 0, 0, and the end point is AB. So the difference between this notation and using just simple parentheses, this is just a point. But this is a vector whose initial point is 0, 0, and its end point is AB. So in this context, there is a difference between these two notations. So using parentheses, and AB is just a point. And the notation that we just introduced is a vector. The initial point is 0, 0. The end point is AB, I'm sorry. A vector, this is a vector whose initial point is 0, 0. And terminal point is the point AB. Let me give an example, a very simple example. And draw the vector 2 and 4. And suppose we have a coordinate system. This means the initial point is 0, 0, and the end point is 2 and 4. So suppose this is 2 and 4. Now the vector which connects the initial point to that point 2, 4. So this was the initial point 0, 0. It was a point. I use parentheses. The terminal point, again, I use parentheses 2, 4. But this thing that, or this arrow that connects 0, 0 to 2, 4 is not a point anymore, is a vector. Vector 2, 4. Okay. Okay, so now you might wonder that if the initial point is not the origin of the coordinate system, how can we use the same notation to show a vector? So let me give an example. Let P be the point to 1 and Q be the point four and 6. Show the vector PQ using this notation that we just used in the previous example. So what numbers should I put inside this? What are the two numbers? So the question is, in fact, let me rephrase this question. So we have a vector with the initial point of 2, 1. So the initial point is here. The end point is 4 and 6. So like here, so this is P, 0.21. This is Q, 0.46. And I want to show this vector PQ using the notation that we talked about earlier. But that notation, in that notation, we assume that the vector starts from the origin of the coordinate system. But there is a vector equal to the vector PQ, which initiates from the origin. So from the origin, I draw a vector parallel, whose line is parallel to PQ, showing the same direction of the same length. It will end here. So the initial point of this is 0, 0. Can you figure out that what would be the end, the terminal point here? Terminal point that this vector ends as, if you need time, you can pause the video and try to think about this. As some of you have already probably guessed, that point is 2 and 5. So let me give a name to this vector, u. Of course, u is equal to the vector PQ. U start from 0, 0, ends on 2 and 5. So the way that we show PQ is in this notation, we put 2 and 5 in those blank spaces. Let me make a general statement if there is any confusion about this example. You can look at the general statement and that clarifies more. So this is a note. So consider the points. We have 2 points. The initial point P, suppose its coordinates are, as you know, there are 2 numbers. Suppose they are x1, y1. I want to make a general statement, so I use parameters for that. And the endpoint or the terminal point of the vector is x2, y2. Then one way to show the vector PQ is this notation. The first coordinate will be x2 minus x1. And the second coordinate is y2 minus y1. So y2 minus y1. To clarify this, let me give a question. I make it a multiple choice question and you should decide that which one is the correct answer. Okay. So next example is a multiple choice question. Consider these 2 points. Consider P, which is 3, 5, and Q, which is 1 and 8. Then the vector PQ is equal to, so which one is the correct answer? So I have 4 answers, but one of them is the correct answer. The first one is A is equal to, and in all of them, I use this notation. So one of them is 2 and 7, 2 and 3, minus 2, minus 3, minus 2, and positive 3. So this vector PQ is equal to which of these vectors? If you need a little bit of time, you can pause the video and do the calculation and then compare your answer to my answer. So to answer this, I can I can use this note that if the initial point is x1, y1, and the terminal point is x2, y2, the vector PQ in that notation has the first coordinate of x2 minus x1, and the second coordinate is y2 minus y1. So the first point has the coordinates of x1, y1, second coordinate of x2, y2. So using the notes that we just talked about, x2 minus x1, 1 minus 3, and y2 minus y1, 8 minus 5. 1 minus 3 is negative 2, 8 minus 5 is 3. So among these answers, obviously D is the only correct answer. So the advantage of this notation is that this is a vector connecting the origin to the point minus 2 and 3. And that vector is equal to the vector that connects the initial point of 3 and 5 to the terminal point of 1 and 8. Okay, another thing that we need to talk about is as I mentioned, the length or the magnitude of a vector. So the length or magnitude of a vector, obviously. The easiest situation is when we have a vector connecting the origin to some point AB. So suppose this vector connects the origin to point AB. And as you know, we showed this by the notation that we have like this. So the length of these vectors, so let me give a name to this vector. Suppose I call this vector U. So the length of this vector obviously is the length of that line segment between the origin and the point AB. And for finding that line segment, it's like a distance formula. You know, distance formula from courses like pre-calculus or even more elementary courses. So, and you know that the length of that line segment is radical a squared plus b squared. The line segment that connects the origin and the point AB. Using Pythagoras theorem, it's going to be radical a squared plus b squared. The notation that we use for showing the length is like absolute value sign. Like here, but we don't, for the vectors, we don't say absolute value, we say length or magnitude. So this means, this notation here means the length or magnitude of the vector u. In this case, it is radical a squared plus b squared. Or I could have written this definition like the length of this vector AB is equal to radical a squared plus b squared. But sometimes the vector is not given in this standard form that it's initiating from the origins. Maybe the initial point is a point different from the origin. So how can we come up with a formula? So suppose we have P with the coordinates of x1, y1, Q with the coordinates of x2, y2. And I want to find for the vector PQ, I want to find the length, this absolute value sign. How can I do that? First of all, for the vector PQ, I find the equal vector which initiates from the origin, as we have talked about this before. And based on the notes that we discussed before, this PQ is x2 minus x1 and y2 minus y1. And we know how to deal with the length of the vector if it is given in this standard form that initiates from the origin of the coordinate system. So the length of PQ is going to be radical of this first coordinate squared, x2 minus x1 squared, plus the second coordinate squared, radical, I'm sorry, is that parentheses, y2 minus y1 squared. So that's how we find the length of a vector if the initial point and the terminal point are given. It is like very much distance formula. In fact, in the distance formula, we calculate the length of the hypotenuse of a right triangle. So let's see an example. Suppose P is consisting of the point 4 and -1, and the Q is 0.3 and 4. Compute the length of the vector PQ. Just for clarification, give an exact answer, meaning that if there was a radical involved and the radical cannot be simplified more, just leave it as a radical. Of course, if the radical can be simplified, we have to simplify, but if the radical cannot be simplified, leave it as a radical. That's the meaning of an exact answer. So please try this on your own before you see my solution. So here, this has two coordinates, x1. So P has two coordinates, x1, y1, and the Q has two coordinates, x2, y2. Based on the formula that we discussed on the previous slide, this is going to be equal to radical of x2 minus x1 squared plus y2 minus y1 squared. x2 3, x1 4, y2 4, y1 negative 1. Three minus 4 is negative 1. Negative 1 squared is 1. 4 minus 1 is 4 plus 1, which is 5, and 5 squared is 25. 1 plus 25 is 26. So under the radical, I have 26. As an exact number that cannot be simplified more, so the radical stays, and this will be the final answer. So the length of that vector PQ is radical 26. Let me add one part to this example, and that part is draw the vector PQ. For simplicity, draw PQ such that the initial point, instead of P, it is the origin, 0, 0. So PQ is the initial point is P, the terminal point is Q, but you know that I can draw a vector initiating from the origin, which has the same length and the same direction as PQ. That will be also equal to PQ. And here I want to draw that copy of PQ, which is not exactly initiating from P, but initiating from the origin. So to do that, to be able to find that, first I need to write PQ, the vector PQ, in this notation. As you might remember, it was the first coordinate was x2 minus x1. The second coordinate was y2 minus y1. x2 minus x1, 3 minus 4. y2 minus y1, 4 minus negative 1. So that vector initiating from the origin is going to be -1, 5, this vector. So if I want to draw this in a way that the initial point is 0, 0, So the initial point is 0, 0. The terminal point is point -1 and 5. So -1 and 5. And that will be this vector. Some friends, they might say that, but PQ initial point was P and terminal point was Q. Yes, but I wanted something equal to that, whose initial point is 0, 0. Although this, the vector that you see on the screen, which initiates from 0, 0, looks different from PQ. In fact, it is equal to PQ because they have the same length and the same direction. So this is the vector -1 and 5. And vector -1 and 5 is equal to the vector connecting P to Q.